Welcome back. This is Amit Sinha. For 2 lectures, our forces have politely balanced. Today, we let them win. F equals ma, handled properly, what Newton's laws actually claim, diagrams as a discipline, and machines built from rope and pulley that will surprise you. An old paradox, older than Newton's ink. A horse pulls a cart. By Newton's own third law, the cart pulls back on the horse exactly as hard. Equal and opposite. So the pulls cancel and nothing can ever move. Yet horses do pull carts. Somewhere in that innocent argument hides a mistake, and it is the single most common mistake in all of mechanics. And here is a stranger promise. A painter stands on a hanging platform, grips a rope, and pulls downward. She rises. Baron Munchausen claimed he lifted himself by his own hair. Physics laughs at him but smiles at her. By the end of this lecture, she will hold 100 kilograms aloft with a 50-kilogram pull, and you will know exactly where the factor of 2 came from. The plan. Newton's 3 laws, stated carefully, because the care is where the physics lives. Momentum, the deeper quantity underneath. Free body diagrams, the discipline that makes hard problems routine. Then, the machines, a train of blocks, the painter's hoist, a double Atwood, and a wedge that scoots out from under its own block. Along the way, a sneaky paradox about massless pulleys, and to close, a monkey racing its own counterweight. Newton's first law, word for word, because every word is load-bearing. A body remains at rest or in motion at a constant speed in a straight line, unless it is acted upon by a force. Watch it live. The puck, untouched, glides at constant velocity forever. Nothing keeps it going because motion needs no keeper. That one sentence buried 2,000 years of Aristotle. This law is not the second law with force set to 0. It is the stage on which the second law performs. It defines the honest viewpoints, the inertial frames, where acceleration means force and nothing else. Stand in a braking train and the puck seems to accelerate with no force in sight. Wrong frame, not wrong law. Lecture 29 settles that score. And read the fine print. Acted upon by a force means a net force. A book on a desk feels gravity and the desk's push, yet its velocity never changes. Balanced forces count as none. Uniform motion is a state of being, not a process to sustain. Force explains change of motion, never motion itself. That is the entire revolution. Law 2. At any instant of time, the net force on a body equals the body's mass multiplied by its acceleration. Equivalently, the rate at which the body's momentum is changing with time. As a formula, F equals ma. 2 readings of one law, and the momentum reading earns its own slide in a moment. Read it as a recipe. The left side is the world's business. Add up every push and pull on the diagram. The right side is the body's response. And notice what the law does not tell you: how strong gravity pulls, what a spring does. Those are separate force laws. F equals ma is the exchange rate between them and motion. Watch the exchange rate at work. The same shove applied to a puck of double the mass buys half the response. Mass is the stubbornness in the equation, the refusal to change velocity. That is all mass is here, and it is measured, not assumed. Law 3. If 2 bodies exert forces on each other, these forces have the same magnitude but opposite directions. Every push is a handshake. Press on a block, and it presses back on you, exactly as hard, at the same instant, no matter which of you is bigger, heavier, or moving faster. But read the fine print, because it is the whole law. The 2 forces act on different bodies, one on you, one on me. They can never cancel because cancellation is something that happens on a single body's ledger, and these two entries sit in different books. And that dissolves the horse. The cart's pull back on the horse is real, but the horse's motion is decided only by forces on the horse. The cart's drag backward and the road's grip forward. The horse leans, the ground pushes, the pair wins the ledger. The paradox was bookkeeping fraud. Two different bodies' forces added on one page. Now the deeper version. Define momentum, P equals mv, mass times velocity. Newton never wrote F equals ma. He wrote that force is the rate of change of momentum, F equals dp by dt. For constant mass, the two statements agree exactly. But when mass changes, a rocket burning fuel, a growing raindrop, the momentum form is the one that stays true. File that away. Lecture 12. We'll collect. Watch what the third law buys us. Two carts about to collide. During the crunch, each feels one internal force, and the pair is equal and opposite. Add the two momentum rates, the internal forces cancel in the sum, always, instantly, exactly. So the total momentum of the pair can only be changed from outside. If nothing external pushes, d of p1 plus p2 by dt is 0. The total is frozen, while the parts trade. Watch the bars in the collision. Each cart's momentum lurches. The goal total never moves. This is the third law's true face. Not a slogan about reactions, but a conservation law. Momentum is the currency of mechanics. Forces merely move it between accounts. Every collision, every explosion, every rocket in Lecture 12 runs on this one line. Now the discipline. Hard mechanics problems are not hard because of calculus. They are hard because of bookkeeping. The free body diagram is the bookkeeping, and it has 4 rules. Rule 1. Isolate a single body and draw it alone. Rule 2. Draw every force acting on it, and nothing else. Rule 3. Partner forces belong on other bodies' diagrams, never on this one. Rule 4. Only then write F equals ma, one axis at a time. Watch the rules dismantle a mess. A block stacked on a block, dragged across a frictionless floor. One picture, 5 forces, hopeless. So explode the picture, each body gets its own card. The top block's card carries its weight and the push from below. The bottom block's card carries its weight, the floor, the pull, and the top block pressing down. Suddenly, every arrow has a home. Rule 2 hides a test. Every real force has a source you can point at, a rope, a surface, the earth. If you cannot name the object doing the pushing, the force does not exist. The famous imposter is the force of motion, an arrow drawn forward just because the body moves. Motion is not a force. Strike it out. No source, no force. Say it before every problem. The diagram is not a sketch of the situation. It is a contract with the second law. Every arrow on the card, and only the arrows on the card, may enter the equation. The problems ahead are won and lost right here. Our machines are built from string, so ask the humble string what it carries. Last lecture we sliced a heavy rope and found its tension changing along its length, carrying the weight below each cut. Now, let the rope's mass go to 0. A slice of nothing needs no net force, so the tension must come out the same on both sides of every cut, one number, T, along the whole string. Run the same argument over a pulley. If the pulley's wheel is massless and spins freely, the string slides over it with tension unchanged, T in on one side, T out on the other. A pulley is a device for turning a force around a corner without spending any of it. Hold that thought. There is a small paradox buried in it, and we will dig it up in a moment. Strings carry one more law, and it is pure geometry. The string does not stretch. Write the total length as a sum of segments, and that sum is constant forever. Differentiate the sentence twice, and geometry starts dictating accelerations. This is called the conservation of string, and it is the honest name for what pulleys do to motion. The classic test bed, the Atwood machine, two masses on one string over one pulley. The string gives A1 equals minus A2, one goes up exactly as the other comes down. Each mass gets a card. The heavy side, M2G down, T up. The light side, T up, beats M1G, same T on both cards, courtesy of the massless string. Two equations, two unknowns. Add them. T cancels the acceleration. A equals m2 minus m1 over m2 plus m1 times g. Substitute back. T equals 2 m1 m2g over m1 plus m2. The imbalance drives. The total mass resists. We tortured these formulas with limiting cases back in lecture 1, and they passed every trial. Now we put them to work. So dig up that paradox right now. A massless pulley redirects a string, tension T comes in, tension T goes out, and its axle must be bolted down against a pull of 2T. So this object with no mass at all is exerting and receiving very real forces. But F equals ma and m is 0. Should not zero mass mean zero force? Unwind it slowly. F equals ma with m0 says the net force is 0 and says nothing else. The individual forces on the pulley can be as large as they like, provided they cancel, two strands pulling down and out, one axle holding on, three arrows closing into a perfect triangle. Zero mass forbids leftover force. It does not forbid force. And that is not a nuisance. It is a gift we will spend for the rest of this lecture. The massless string, same tension everywhere, net force 0 on every slice. And when a hanging pulley turns up inside a bigger machine, its zero net force will donate a free equation at exactly the right moment. Every massless part hands you one free equation before any physics begins. The paradox was a theorem wearing a disguise. Real pulleys, of course, have mass, and then the two tensions genuinely differ. That difference is what spins the wheel, and it needs the machinery of rotation, moment of inertia, waiting in lecture 21. Until then, massless is not an approximation to apologize for. It is a license to print equations. First machine. A locomotive force. F drags a train of 5 identical blocks, mass m each, across a frictionless floor. The couplings are short, massless strings. Easy question. How fast does the train accelerate? Better question. What does each coupling carry? The answer hides a technique worth the whole problem. For the acceleration, do not touch the couplings. Draw the boundary around the entire train, 5 blocks, one system, total mass, 5m. The couplings are now internal, and internal forces cancel in pairs by the third law. One card, one force, the acceleration. A equals F over 5m. The couplings never even appeared. Now for what the couplings carry, cut where you want the answer. Slice the train in front of the rear 3 blocks and take everything behind the cut as one system. 3 blocks, mass 3m, and exactly one force crosses the cut, the coupling tension, T3. Its card reads T3 equals 3ma, which is 3/5 of F. Slide the cut down the train and the pattern unrolls. Each coupling carries just the mass behind it. 4/5 of F, then 3/5, 2/5, 1/5. A staircase descending toward the caboose. The last coupling hauls a single block and carries a single fifth of the locomotive's pull. Check the shape of the answer. The front coupling works hardest. The rear one loafs. If the engine pulled from the back instead, the staircase would simply mirror. And let the blocks shrink and multiply. 5 to 50 to 5,000. The staircase smooths into a straight ramp. That is precisely the heavy rope from last lecture, tension climbing linearly from free end to pulled end. The discrete and the continuum shake hands. The technique is the takeaway. A boundary is a question you ask the problem, draw it around everything, and internal forces vanish. Cut it where you are curious, and exactly the force you wanted walks across it. You choose what the second law talks about. Remember lecture 3. Choosing pivots to kill unknowns? Same instinct, new weapon. Now the painter, as promised. She stands on a platform hanging from a rope. The rope climbs from the platform over a pulley bolted to the ceiling and comes back down into her hands. Painter, 80 kilograms, platform, 20. She hauls downward on her end. The question, how hard must she pull to hold the pair aloft or to rise? Try the diagrams one body at a time. And it is a thicket. The rope pulls her hands up. The platform pushes her feet. She presses the platform. Tension everywhere. All true, all slow. Instead, use the train's trick backward. Draw one boundary around painter, platform, and the rope's lower loop, and count only what crosses it. 3 things cross. Gravity, pulling down on the full 100 kilograms inside, and the rope, which crosses the boundary twice, once on each side of the pulley, each strand hauling straight up with the same tension. T. Once as the strand tied to the platform, once as the strand in her grip. The card reads 2T up, 1000 newtons down. To hover, 2T equals 1000 newtons, so T equals 500. Her hands supply a 50 kilogram pull, and 100 kilograms hangs from it. There is the factor of 2, and it was never magic. She pulls on the system through both ends of the rope, and the pulley lets her. Pull harder, say 600 newtons, and the surplus of 200 buys acceleration. A fifth of G, upward she goes. One more surprise is hiding in her feet. Draw her card alone, weight, 800 down, rope in her hands, 500 up, so the platform need only push 300. A scale under her feet would read 30 kilograms. By hauling her own weight, she stands featherlight on her own floor. Every rescue hoist and dumbwaiter runs on this arithmetic. And notice what the boundary bought. A helper standing on the ground, hauling the free end, gets no factor of 2. Her rope crosses the system boundary once, and she must supply the full 1000 newtons. The advantage belongs to the rider, because the rider's pull crosses her own boundary twice. Where you draw the line literally changes the force you need. Next, pulleys hanging from pulleys. A fixed pulley, P1, carries mass M3 on its left. Its right strand ties to the axle of a hanging pulley, P2, whose own string carries M1 and M2. To keep the bookkeeping honest, we measure everything with one ruler, a y-axis pointing straight down from P1's center. Every moving piece gets a coordinate. The upper string first. Its length is y3 plus yp2 plus the fixed arc over the wheel and string does not stretch. The sum is constant. Differentiate once. v3 plus vp2 is 0. Differentiate again and the accelerations lock. a3 equals minus ap2. Whatever m3 does, p2 mirrors it instantly. Now the lower string, measured from the moving pulley, its 2 hanging pieces are y1 minus yp2 and y2 minus yp2, and their sum is constant. One derivative, v1 plus v2 equals 2 vp2. A second derivative locks the accelerations, a1 plus a2 equals 2 ap2. The average of the lower pair rides along with its pulley. Count what geometry has given us. 3 unknown accelerations and 2 equations binding them. Whatever remains must come from the forces themselves. Hold these 2 constraints tight. The next slide sends in the tensions. Now, the forces. Every strand of the lower string pulls up with one tension, T2, the upper strand pulls with T1. Each mass carries its weight, and the hanging pulley P2 is massless, so the net force on it must vanish, T1 equals 2, T2. The middleman donates an equation exactly as promised. Cards, 1 per mass, with down as positive to match our axis. M1, weight down, string up, so M1G minus T2 equals M1A1. M2 reads the same with its own numbers. M3 hangs from the upper string, M3G minus T1 equals M3A3. 3 equations, 2 constraints, 1 pulley relation. The system is closed. Turn the crank, but choose the first target wisely. Chasing an acceleration first drags every equation along for the ride. The tension is the better prey. The pulley relation kills T1 immediately. The constraints kill 2 of the accelerations, and the 3 cards collapse onto a single unknown. T2 falls out first. Then every card hands back its own acceleration. 1 line each. Solve for the tension, then read off the motion. Here is the full harvest, cleaned up. 1 tension rules the lower string, and twice it rules the upper, and each mass wears its own acceleration. 3 different numbers bound by the 2 constraints. Do not memorize the expressions. Read their shape. Everyone is a ratio of imbalance to total inertia, the Atwood signature scaled up. Now ask what the upper string actually feels. Eliminate everything below the hanging pulley, and the whole lower assembly acts on the upper string like a single block with an effective mass, 4m, 1m2 over their sum. The harmonic pattern again, the same algebra that combined springs in series last lecture. Numbers. And the surprise. Hang 1 kilogram and 3 kilograms on P2. The effective mass is 4 times 3 over 4, exactly 3. Balance that against 3 kilograms on the far side and the machine stands still. 4 kilograms of hardware held level by 3, while the 1 and the 3 inside accelerate merrily. Why does the heavy side not win? Because the lower masses are moving, the 3 falls. The 1 rises, and the string of that internal motion settles at 3/4 of the cargo's weight. No more. What a machine weighs depends on what it is doing. Statics would have lied to you, only the diagrams told the truth. The last full machine and the subtlest. A block rests on the frictionless face of a wedge, angle theta, and the wedge itself stands on frictionless ice. Release everything. The block slides down, the face retreats underneath it, and the 2 motions are tangled together. Before any forces enter, we need the geometry that ties them. The cast, briefly, on their cards. The block feels gravity and the faces push. The wedge feels its weight, the ice and the block pressing back. 3 unknowns hide there. The push N, the wedge's acceleration, and the blocks. The cards alone leave us 1 equation short. Geometry must speak. So watch pure motion with no arrows anywhere. In a short time, the wedge scoots right by LW. The block shifts sideways by LX and drops by LY. Relative to the wedge, the block's horizontal progress is the difference, LX minus LW. And to stay on the face, that relative step must run along the slope, tan theta equals Ly over Lx minus Lw. That single line is the missing equation. It holds at every instant, so differentiate it twice and displacements become accelerations. This gives us the constraint Ay equals tan theta times Ax minus the wedge's acceleration. Geometry has spoken. The next slide lets the forces answer. Assemble the machine of equations. The block, along the horizontal, only the normal sideways part acts. The block, vertical, gravity against the normal's upright part. The wedge, horizontal, the reaction sideways part, pushing the other way. And the constraint triangle links the two accelerations through tan theta. 4 lines turn the crank. The algebra folds up neatly, and out comes the wedge's acceleration, mg sine theta cosine theta, all over mw plus m sine squared theta. The numerator is the engine. Gravity's push relayed sideways through the tilted contact. The denominator is the stubbornness, and notice the odd term, the block's mass enters it, wearing sine squared only as much of it as rides the constraint. Interrogate it, like always. Bolt the wedge down. MW, enormous. Acceleration, a W dies, and the block slides at g sine theta, exactly lecture 2's incline. Flatten the angle to 0. Sine kills everything, nobody moves. Stand it up to 90 degrees. Cosine kills the push. The normal force lets go, and the block simply free falls beside an untouched wedge. 3 limits, 3 sanity checks, all clean. And run one quiet check with our deeper law. Horizontally, nothing external pushes the system. Ice is frictionless, gravity is vertical. So the total horizontal momentum must stay 0, block drifts left, wedge drifts right, in exact proportion, and the pair's center of mass falls straight down. The plumb line does not lie. Momentum bookkeeping, auditing the algebra for free. One last machine, small and wicked. Lewis Carroll lost sleep over it. A monkey grips a rope hung over a massless pulley. On the other end hangs a counterweight of exactly the monkey's mass. Everything balances. Now the monkey starts to climb his side of the rope. The old riddle? Does the counterweight rise, fall, or just sit there? Cards. The monkey feels the rope's tension up and his weight down. T minus M. G equals MA. The counterweight hangs from the same string over an ideal pulley, so it feels the same T and its card is identical, letter for letter. Identical equations give identical answers. The two accelerations are equal, always, instantly, whatever the monkey chooses to do. So the counterweight is the monkey's mirror. He climbs, it rises exactly as fast. He lunges, it lunges, he freezes, and so does the weight. Hand over hand, he hauls rope through the pulley, and the weight matches him foot for foot. Monkey and counterweight arrive at the top together. He cannot win, and he cannot lose. The machine forbids both. No numbers needed, the machine is the answer. Two massless parts, string and pulley, donated one equation, the same tension on both sides, and that symmetry does all the work. Check the limit. A monkey who simply hangs is a counterweight himself, and everything stands still. Correct. Keep this riddle, it returns wearing momentum in Lecture 12. The 30-second audit. The train, pull from the rear instead, and the staircase mirrors perfectly, and a train of one block has no couplings and nothing to carry. Correct. The painter let go of the rope and 2t becomes 0. She and her platform are simply a falling body. The formula collapses to free fall, exactly as it must. The double Atwood make the lower masses equal, and the effective mass, 4mm over 2m, is just 2m. The lower pulley locks, dead weight, and the whole rig is an ordinary Atwood. The formula contains its own simpler self. Correct. And the wedge already confessed under interrogation, infinite wedge gives Lecture 2's incline, flat face gives stillness, vertical face gives free fall. Every machine in this lecture, pushed to its edges, lands on physics we had already learned. The audit stays free, and it stays mandatory. 3 ideas to carry forward, 1 body, 1 diagram, every force on the card has a source you can point at, and third law twins never share a page. The boundary is yours. Wrap it around everything and internal forces vanish, or cut it where you are curious and the answer walks across. And constraints are free equations, strings, faces, and massless paths. All legislate before F equals ma says a word. The habit: for every problem from now on, before touching the algebra, draw the boundary that makes the unknowns internal. Lecture 3 chose pivots. This lecture chooses boundaries. It is the same second of thought and it buys the same page of algebra. Next time, force stops being a constant. Drop drag into the second law and F becomes a function of velocity. The law becomes a differential equation, a sentence about change. We will tame the species. A projectile that drifts into vertical fall. The strange truth that a thrown ball strip up is quicker than its strip down. And a skydiver whose chute rewrites the equation mid-flight. Bring your calculus. It finally gets to drive. That wraps up this lecture. This is Amit Sinha. Thanks for watching the Sinha Foundation channel. See you in the next one.